You ever watch an athlete and just wow? A perfect golf swing, a tennis serve that's just a blur, a gravity-defying dunk. It can look like pure magic, right? But it's not. It's physics. And believe it or not, behind every single one of those amazing moments, there's a hidden blueprint, a set of scientific rules that our bodies follow to create all that power. So today, we're going to pull back that curtain and take a look at the science behind the action.
Okay, so here's a weird question for you. What on earth could a blistering tennis serve possibly have in common with a playground seesaw? I know, it sounds kind of crazy. One is this incredibly complex, high-speed, athletic feat, and the other is, well, a toy. But the answer to this question is actually the key to understanding how pretty much all athletic movement works. They're built on the exact same principle.
And that secret is levers. That's right. Your body is this incredible, intricate system of simple machines. Every single bone, every joint, every muscle, they're all working together to form levers that let you do everything from walking down the street to hitting a home run. So to really get it, we need to break down the three parts that make up every single lever in your body.
First up, you've got the fulcrum. This is just the pivot point. Super simple. It's the point in the middle of that seesaw. And in your body, your joints are the fulcrums. Your elbow, your knee, your shoulder, any place where movement pivots, that's your fulcrum.
Okay, so you've got a pivot point, but you need something to make it move, right? That's the effort. This is the force that gets the whole thing going. When you push down on a seesaw, that's the effort. For us, that force comes from our muscles contracting and pulling on our bones. You could think of your muscles as the engine for the entire system.
And finally, there's the load. You might also hear it called the resistance. Basically, this is just whatever the lever is trying to move. It could be a heavy dumbbell, it could be a soccer ball you're about to kick, or, it could even be just the weight of your own arm or leg.
Now here's where it gets really cool. Depending on how you arrange those three parts, the fulcrum, effort, and load, you get three totally different classes of levers. In a first-class lever, the fulcrum is in the middle. Think about nodding your head. For second class, the load is in the middle, like when you push up for a calf raise. And this is a big but. Almost all the levers in our bodies are third class, where the effort is in the middle, like a bicep curl. And there is a huge reason our bodies are designed that way.
And that reason comes down to this fundamental trade-off, a choice between pure strength and pure speed. See, the way our levers are set up decides whether they're good for producing a ton of force or for generating insane velocity. And it all boils down to this concept called mechanical advantage.
So here's the deal. A lever with a mechanical advantage, like that second-class calf raise, is awesome for creating force. You can lift your whole body with a pretty small muscle. The catch? It's slow. On the other hand, our third-class levers, the ones we have everywhere, operate at a mechanical disadvantage. Your bicep has to generate a massive amount of force just to lift a small dumbbell. But the payoff is enormous speed and range of motion at the end of your arm or leg. And that is why you can whip a baseball or swing a tennis racket so incredibly fast. Our bodies chose speed over brute force.
Okay, so we've got the engine, right? The levers that create all that force and speed. But now we need the map. We need to figure out where all this movement is happening. And it turns out that all human motion can be sorted into three invisible planes that slice right through the body.
First up is the sagittal plane. I want you to picture a giant sheet of glass splitting your body perfectly into a left half and a right half. Any movement that goes forwards or backwards happens in this plane. So sprinting, doing a bicep curl, a front flip, that's all happening in the sagittal plane.
Next, we have the frontal plane. This time, the sheet of glass splits you into a front half and a back half. So any movement that's side to side is happening here. Think about doing jumping jacks, or shuffling side to side on a basketball court, or doing a big cartwheel. That's all frontal plane.
And finally, we have the transverse plane. This one cuts you into a top half and a bottom half. This is the plane of rotation. Any kind of twisting motion, swinging a bat, throwing a discus, a golf swing, that all happens in the transverse plane. And you're going to find that most of the truly powerful athletic movements rely a lot on this rotational power. Now really quick, each of these planes has an axis it rotates around. Think of it like a skewer that the movement spins on. So a cartwheel in the frontal plane spins around the sagittal axis, which runs from your front to your back. A forward somersault in the sagittal plane rotates around the frontal axis, going from side to side. And all that twisting in the transverse plane happens around the vertical axis, running straight down from your head to your toes. So we have our levers that create the force, and we have our planes that define the space. Now for the fun part.
Let's put it all together and see how these ideas actually show up in a real, iconic sporting action. This is where the science becomes the spectacle.
Let's go back to that killer tennis serve we started with. So first, the player winds up, right? They rotate their whole torso and arm backwards. That's a huge movement in the transverse plane. The shoulder joint, that's the fulcrum for the whole thing. Then, the chest and shoulder muscles contract, pulling that arm forward. That's a perfect example of a third-class lever trading force for absolutely massive speed at the racket. And finally, the ball and the follow-through fly forward, mostly in the sagittal plane. See? Levers and planes all working together in one explosive movement.
Honestly, once you start to see these building blocks, the levers, that trade-off for speed, the planes of motion, you can never really watch sports the same way again. It's like you've got X-ray vision. You start to see the physics behind every move, and the game goes from being just a spectacle to this amazing masterpiece of biomechanics. So next time you're watching a game, I want you to look for it. When a player jumps for a rebound, can you see that second-class lever in their calf? When a batter swings for the fences, can you spot that powerful rotation in the transverse plane? The blueprint is out there in every single play. What are you going to spot next?